All right, let's move on. We started to discuss tectosilicates in the last class. And these tectosilicates were the parent compounds of all tectosilicates, the polymorphs of silicon dioxide. So we've looked at the forms of quartz. We have looked at tridamite, cristobalite. We have looked at the high pressure polymorphs, coesite and stishovite also. However, all these compounds are just polymorphs of SiO2. They are not silicate in the sense that they have an anionic framework, which is then charge compensated by other cations. So in order to arrange that, we have to substitute at least some of the silicons in the tetrahedral framework by aluminums, because when we have tetrahedrally coordinated aluminum, then formally that framework has a negative charge, and then we can have a counter cation somewhere in the compound. It's not part of the framework. Then we call this counter cation, also often extra framework counter cation. Okay, so we know many tectosilicates. So how do we classify them? And the framework porosity is one of the most common ways how to classify them. So we know the so-called pycnolites, which are very small pores. So for instance, the feldspars are pycnosites. Remember, the feldspar is actually the most common mineral in our Earth crust. So these pores can only accommodate small cations. Then we have the so-called clathrasiles. So they have polyhedral pores with small windows. So these polyhedral pores are large enough to accommodate small molecules and small molecular ions, but these guests are actually entrapped within these pores because of the small windows. So an example of that is ultramarines, ultramarines, which has this composition here. It's the sodium alumosilicate that contains the trisulfide anion. So this is a radical anion, and we will discuss about the exact structure in a moment. So now, then we know the zeolites, and these zeolites now have larger pores, which range typically between 0.3 and 2 nanometers, and they also have open windows, and molecules and ions can enter these pores through these windows. So we can recognize a zeolite through a parameter which is called the framework density, which measures the number of tetrahedral centers. That's basically the number of silicon atoms per 1,000 cubic angstroms. And zeolites have typically framework densities between 10 and 20 tetrahedral centers per 1,000 cubic angstrom. So for zeolite chemistry, the so-called Löwenstein rule applies, and that means that the silicon to aluminum ratio must be larger than 1. So the Löwenstein rule is because of electrostatic reasons. Only when the silicon to aluminum ratio is larger than 1, then we can have either silicon-oxygen-silicon and silicon-oxygen-aluminum bridges, but we won't have aluminum-oxygen-aluminum bridges. So these aluminum-oxygen-aluminum bridges are electrostatically unfavorable because both aluminums formally carry a negative charge. So these negative charges in the framework come to close when these bridges are present. So they are not encountered in nature. Okay, let us look at a few concrete examples for each class of tectosilicates. So I previously mentioned the feldspar is the most abundant mineral on the Earth's crust. So we should probably know its structure. So here's its structure, and structure is a little bit similar to that of coesite. So you can conceive this feldspar structure as zigzag paired chains. Okay, so see here we have chains of these yellow tetrahedra and these chains of these green tetrahedra. Okay, and these chains are paired in the sense that they are sharing corners. You see that in these chains you have four-membered rings. So you see four-membered rings here and here and here, and then you have additional four-membered rings perpendicular to that. So here and here and here over there you see actually these four-membered rings from a different perspective. So you see that in these four-membered rings, two tetrahedra point up and two tetrahedra point down. So you see that in such a four-membered ring here, you have the same motive. You have two tetrahedra, these two that point up, and two tetrahedra, these two that point down. So now these zigzag pair chains are arranged in a three-dimensional structure. So you see this over here. And over here, you can actually see how you can also view the feldspar structure from a different perspective. So you see here that you have four-membered rings in yellow and four-membered rings in blue. So the yellow colored one belong to a layer, so they are in one plane, and the blue ones are also in one plane, whereby the blue plane lies below the yellow plane. Okay, so now you see that within a plane you have again four-membered rings, okay, that are interconnected to form chains. Okay, so these four-membered rings are these four-membered rings here. Okay. Now, these chains of four-membered rings, they are interconnected with blue chains of four-membered rings that are in the layer below. And you see that this creates additional four-membered rings that are composed of, well, two yellow tetrahedra and two blue tetrahedra. And these four-membered rings here, they correspond to these four-membered rings here. Okay, so here in this view, we are looking actually along the B direction, and you see the A direction is here and the C direction is here. So here in this zigzag chain, we look along the A direction. So the A direction would be here, and therefore all these four-membered rings here, you see here, they are arranged in the A direction. Okay. Now you see here the same, and in this view, we again look along the B direction. Okay, but here you see these zigzag chains, these ones here more clearly because they're all of the same color. Okay, so we have these four-membered rings, these ones here, connected, interconnected, forming more four-membered rings. Okay, whereby these four-membered rings then perpendicular to these four-membered rings. Okay, and then these chains are interconnected in order to form a three-dimensional structure. All right. Okay, so now we also have countercations. So now where are the countercations? You can see where they are located most easily when you look along the A direction. Okay, So now along the A direction, we see now again 4-membered rings, okay, that are interconnected. And you see that in these 4-membered rings, 2 tetrahedra point up and 2 tetrahedra point down, okay? And these 4-membered rings now correspond to these 4-membered rings here, you see, with 2 tetrahedra point up and 2 tetrahedra point down. All right. Now, from that perspective, you can see now that there are additional rings, okay, which are larger, okay. So these are actually these ones here, okay. These more oval-shaped rings, and these larger, more oval-shaped rings can now accommodate the countercations, which can be either potassium, sodium, or calcium, okay. So this is how you can overall understand the feldspar structure. All right, so this is an example of a highly condensed tectosilicate. Now let's make the pores more open. And go to the example of ultramarine, which is also an interesting mineral, partly because it is such a nice blue color, okay? For that reason, it has also been used as pigment, and you can also make synthetic variants of ultramarine blue that you can use as a pigment. So what is its structure? And how can we explain the blue color? So we can actually see this here in this view. So let's do a new share. Screen share, and I hope that I could find this. Not sure, so we have to go to this here. Yes, let's make a new share. Choose this one and that one. And now you see here in the website that I mentioned to you previously already at some point, chemtube3d.com, the three-dimensional structure of the ultramarine. You see that this is a cubic structure, whereby you have here tetrahedra on the faces, on the 6 faces of that cube. And you have actually exactly 4 tetrahedra arranged in a square on the square faces of the cubic unit cell. Okay, so now these squares, they build a cage. Okay, and within that cage you have S3 minus anions. So these are radical anions, which explains the blue color. So in addition to the center of the unit cell, you also have these S3 minus ions on the corners of that unit cell. So essentially, you have a body-centered cubic arrangement of these S3 minus anions. Okay. So now you see that the pores are relatively large. They're about 0.3 nanometers wide, but the windows are only made of these 4-membered rings and 6-membered rings here. So they're relatively small, and that means that the S3 minus ions are actually entrapped in these pores. And that is also stabilizing these S3 minus ions. They cannot go in and they cannot go out, but also no other molecules can go inside of these cages and perform a chemical reaction with these S3 minus anions. For instance, oxygen could potentially oxidize these S3 minus anions. But there's no kinetic accessibility for oxygen to these anions. Therefore, these anions are quite stable. So in such a silicate structure, you can therefore stabilize otherwise quite reactive molecules or molecular ions like S3 minus. Okay, so see here on the left-hand side, you can actually rotate these structures. So when you actually rotate this way, you can clearly see here these 4-membered rings of silicon atoms. When you rotate this way, okay, you can see that there are also 6-membered rings. Okay, and these 6-membered rings, they stand perpendicular to the body diagonal that goes through the cube. Okay, now let's go back to the PowerPoint slide. I have to change my screen sharing again. And let us go directly to the last class of compounds, which actually has the most industrial applications. And that is the zeolites. So zeolites have even larger pores, and now also the cage windows are wide enough so that ions and small molecules can enter and leave these pores. So I would like to give you a brief historic perspective on the zeolites. So zeolites were discovered by A.F. Grönstedt in the year 1756. They're actually quite old class of compounds. And the first zeolite that was discovered was the so-called stilbite. Okay, and what was amazing about this kind of mineral was that when you heated it, all of a sudden, steam was coming out of that rock. And of course, back at that time, people had a very limited idea about the structure of minerals and compounds in general. So the fact that when a rock was heated, all of a sudden a lot of steam would come out of the rock was quite an amazing phenomenon. So that property also gave the zeolites their name. So zeolites actually comes from zeo, that's the Greek word for boiling, and litos, which means stone. So zeolite essentially means boiling stone, and it is a property of the first zeolite that was discovered, the stilbite. All right. Now, how can we explain that property from today's standpoint? Well, today we know that the zeolites have large pores. They contain counterions in the pores, but these pores are also large enough to accommodate water that actually hydrates these counterions in these pores. Now, when you heat the zeolites, then that the coordinative bond between the counterions and the water just breaks, and the water comes in form of free water out of the zeolite pores, and that's what makes this rock actually steaming. Okay, so in the following, many more zeolites were discovered, and here is just a brief list of them. So many zeolites are occurring in nature as minerals, but many zeolites were also synthetically made, especially in the from the 20th century on. So today we actually know quite many zeolites, so essentially hundreds of zeolites. Therefore, specific, well, nomenclature for zeolites has evolved that orders these zeolites according to their structure, and this is documented in the so-called Atlas of Zeolite frameworks. So in the following, would briefly discuss how these zeolites are categorized in the Atlas of zeolite framework types. So first of all, we need to define what we mean by a framework type. So by a framework type, we name a specific structure, okay, but that structure does not necessarily equate in actual material, okay. So in an actual, we can have several actual materials associated with a particular framework type because we can occupy, well, the sites within that framework by different elements, okay. So of course there is silicon, but that silicon can be, for instance, replaced by aluminum. It can also be replaced by other elements such as phosphorus, arsenic, gallium, gallium, germanium, boron, beryllium, etc. Okay, so now a specific framework type is defined by a specific framework type code, which is made of 3 letters. So that framework type code is usually derived from an abbreviated name that defines a material that belongs to that particular framework type. And the name is often associated with the discoverer of the respective material. So for instance, we have a code which is named LTA, which actually stands for Linde Type A, whereby Linde is a company. It's a gas company, a German gas company. The full name is Zeolite A. That's basically the name the company has given that zeolite. So another framework type code, for instance, LTL, which stands for Linde Type L. In some cases, the framework type code is also derived from a mineral name. So that's, for instance, the case for the FAU framework type code, which is derived from the mineral faurisite. So MFI, for instance, is derived from ZSM5, which is a material which was discovered by mobile oil, and it stands for zeolite zircony mobile 5. So that's the full name. Okay. Then we have, for instance, CLO. You see that CLO has a dash or hyphen. So that hyphen indicates that we have an interrupted framework. That means that you do not only have terminal oxygens, but bridging oxygens, but also terminal oxygens. So CLO stands for clavierite, and the associated full name would be 4-leaf clavier-shaped pore opening. Okay. So here as a last example, we have BEA. So BEA stands for zeolite beta. You see here that's the BEA symbol has a star in front of it, so that star indicates that you actually have a disordered materials. So some crystallographic sites within that material are not exactly well defined, but you have actually a disordered structure, partially disordered structure, we should say. All right. So we can describe zeolites in terms of secondary building units, whereby a secondary building unit is defined as a finite or infinite. That means chain or layered-like component units that fully describes the zeolite. Okay, so we're assuming that the entire framework is made of one type of that secondary building unit only. Okay, so many different types of secondary building units possible. So here are a few of them. So it can be, for instance, just rings of a different number of members. So 4 rings, 5 rings, 6 rings, or 7 rings. We can have cage type secondary building units. We can have also more complicated building units like this for one building unit, where we have basically a square, which is attached to a single silicon tetrahedral center. And that can also be the only, well, secondary building unit the zeolite is made of. Or we can have also building units with shared rings, for example. So here we have 2 pentagonal rings that are shared with each other. So this is called 5-3 because we only count this silicon tetrahedral centers once. So if we define that ring to contain the first 5 silicon atoms, okay, then the second ring has only 3 additional members, hence the name 5-3. So important are also composite building units in zeolites. So these actually, in my opinion, are most helpful in order to understand the overall zeolite structure. So here are examples, 2 examples, the so-called alpha cage and beta cage, respectively. So in these composite building units, only the center of the tetrahedra are shown for clarity, not the entire tetrahedral building units themselves. Okay, so you see here, for instance, in this alpha cage, you have here 4-membered rings, 6-membered rings here, and 8-membered rings. Okay, while in the beta cage, you have only 4-membered rings, 6-membered rings. We have actually encountered the beta cage already. We have beta cages in the ultramarine. Okay. All right. Then we also know so-called super cages, and in these super cages, we then have multiple composite building units fused together to indicate even larger pores. So, for instance, you can see here a super cage in the FAU framework. So in this case, you see that we have multiple beta cages fused together to form this even larger pores. Okay, whereby these beta cages are indicated by these light blue hexagons here. All right, so here just a few more examples. So this is the LTA structure, while this is the FAU structure. So both contain beta caches, but these beta caches are interconnected differently. So you see in the LTA structure, these beta caches are interconnected via the 4-membered rings. Okay, so you have essentially a green, this green cube interconnecting these red beta caches, whereas here in the Fourier site structure FAU framework, we have, as we actually already saw before, the beta caches interconnected via these hexagonal prisms, which are also indicated here in green. All right. All right. There are often multiple views on the same structure being possible, depending on, and you choose these views depending on which structural feature of the zeolite you actually want to emphasize. So, for instance, in the LTA structure, you can also define alpha caches. So, why is that? We can walk back, and we actually see that, well, the pore here, which you see actually due to the interconnection of the beta caches, can be defined as an alpha cage. Okay, and then you can describe the structure also in terms of the interconnection of alpha cages. Okay, and in this view, you would just fuse the alpha cages together via now these octagonal faces. Okay, so these alpha cages would share these octagonal faces in 3 dimensions. So this gives you a different perspective on the structure. All right, you can represent the structure differently. So in the most simple case, you can just indicate the silicon tetrahedral centers and then connect the silicon tetrahedral centers with lines. That usually provides the greatest clarity, but you should also keep in mind that, well, each point here actually just represents the center of a tetrahedron. So you can also show the entire tetrahedra if you want to, and this is actually shown here. So this gives you a more fuller picture, a more comprehensive picture, but that goes to some extent a little bit at the expense of the clarity. All right, so now here just 2 more examples of 2 strongly related zeolite framework types that in this case contain both alpha caches. You see again here the alpha caches of the LTA structure. So there's a related structure to that, but the RHO structure, in which these octahedral phases are not directly fused together, but you see that they are actually separated from each other by an octagonal prism, which sits in between the alpha caches. You can see that you can very easily understand from this picture that these pores here in between the alpha caches are smaller for the LTA in comparison to RHO structure, and that the RHO from the RHO structure you would expect a smaller framework density and is more open structure overall. Okay, so from that you can see that the channel systems within a zeolite is important, and because of that there's a specific denotation for these channel systems in zeolites. there's also a specific nomenclature to that I would like to discuss briefly in the following. So it is indicated in the nomenclature, you indicate the channel direction relative to the axis of the material. So you place the direction in between these smaller and larger symbols to indicate that these channels also exist in all symmetry related directions. So for instance, when you have a cubic structure and you indicate the 1, 0, 0 direction here, then that means that also you have the same channel type in the 0, 1, 0 direction as well as the 0, 0, 1 direction. Okay, if you place the direction in brackets, then that means you have that channel really only in that particular given direction. Okay, if you place a particular sign in front, then that means that the channel direction is actually perpendicular to the direction you give here within the brackets. Okay, so you also indicate how many tetrahedral centers are within a ring that forms the channels. Okay, you also give the free diameters of the channels in angstrom, and you give by the number of asterisks whether the channel is 1, 2, or 3 dimensional. So if there's 1 asterisk, it means 1 dimensional. If there are 2, then that means 2 dimensional. If there are 3, then that means 3 dimensional. Okay. Then you can indicate using a double arrow, sorry, that the channel systems are interconnected. Yeah, so they are basically forming a more highly dimensional channel system because of the interconnectedness. A vertical bar that indicates that there is no direct access from one channel system to the other. So these channel systems are independent from each other. Okay, so now let's go apply these rules to a number of cases in order to get a little bit more life into that. So here, for instance, you see the channels in the LTA structure. So the channel system is denoted as 1, 0, 0, 8, 4.1 times 4.1. And you see 3 asterisks here. And in the atlas of zeolites, you would also see the channels depicted here together with the channel diameters. Okay, so we see that these channel diameters are 4.1 times 4.1 angstroms in both directions, and we have overall 8-membered rings here. That means that the channel consists of 1, 2, 3, 4, 5, 6, 7, 8 tetrahedral centers. So these channels run along the 1, 0, 0 direction, but because we have these larger and smaller signs here, we also know that these channels exist in the 0, 1, 0 and the 0, 0, 1 direction. We further know that these channels build an overall 3-dimensional pore system, indicated by these 3 stars here. All right, so here is another example, and here you see the channels in the LTL structure. So here we have 0, 0, 1 in brackets, and that means that we now have these channels only in the 0, 0, 1 direction, but not in another direction. That also directly implies that our channel system is 1-dimensional, indicated by this asterisk here. So in this case, the channel has 12 members, indicated by this bold 12 here. And because we have more members, the channels are also overall larger. So they are 7.1 angstroms in all directions. All right. Here is another example, the example of off-red-tide, OFF. So in this case, we have a more complicated structure. We have a structure with two different channel systems. Okay. Or two different channel types. So we have here channels that run in 001 direction, and they run in 001 direction only because of these brackets here. So this 12 here indicates that we have 12 membered rings made of 12 tetrahedral centers, and these channels have dimensions of 6.7 times 6 times 8 angstrom respectively. So these channels are one-dimensional. Okay. So then we have another channel type, okay, that also runs, which stands now perpendicular to the 001 direction, indicated by this perpendicular sign here. Okay. And these channels are smaller. They are made of 8 tetrahedral centers that have the dimensions of 3.6 times 4.9 angstroms. And in this case, we have a two-dimensionality. Okay. So that means that we have these channels running in perpendicular to 001. That means that they run along 100 as well as 010. So last but not least, this double arrow indicates that these two channels interpenetrate. Okay, so they stand perpendicular to each other and interpenetrate each other. Okay, one more example. These are the channels of the RHO zeolite framework type. Also here we have two different channels to consider. So you see here the first channel type along 100, but you see that we have also symmetry equivalent directions to consider. So we have channels also along 010 and 001. All right, so this channel has 8 tetrahedral members and has dimensions of 3.6 times 3.6 angstroms. So this is a three-dimensional channel system because it runs in these 3 dimensions. So then we have another channel system, and you see that this channel system is the same as this one. So again, it runs along 100, 010, and 001. It's made of 8 membered rings, and the pore sizes are 3.6 times 3.6 angstroms, and it's 3-dimensional. However, the second one is now separated from the first one, is indicated by this vertical bar here. So you have 2 independent 3-dimensional channel system. Okay, one of this type and one of that type. All right. So I think we can stop at this point. We're a little bit early in time, but I think it's okay to stop at this point. And I just stopped the recording.